Hello friends, welcome to Notebook Videos. In this video, we'll be covering a very important topic called acids, bases and salts. As you grow up, you will learn that acids, bases and salts are a very vital part of a subject named chemistry. And any of you who wants to be a doctor or a biochemist or a scientist would have to learn a lot about them in the future. Once you complete this video, you will not only learn about the properties of acids, bases and salts, but also will be capable of doing some indicator tests. Let's begin this video now with a few things that you see. A bottle of tomato sauce, vinegar, a cup of salt, a pack of chalks and soap solution. Well, if you look at each one of them individually, you will see that each one of them have their own special properties. Starting with the tomato sauce, we see that it is made up of tomatoes that are rich in oxalic acid. Because of the presence of the acid, the taste of the sauce is sour. Similarly, vinegar also tastes sour and is made up of acetic acid. Friends, now let's look at the bowl of salt. The formula of salt is NaCl or sodium chloride. Anything that tastes salty would have the NaCl ingredient. Chalks are typically classified as salts but do not contain NaCl. Instead, they are made of CaCO3. Now if you look at the soap solution, it contains potassium hydroxide, KOH. This is referred to as a base. Any solution that contains negative OH ions has the properties of a base. So friends, let's build a table of differences that lists all important properties of acids, bases and salts. We'll be looking at more examples of acids, bases and salts. And then ways by which they can be differentiated by way of neutralization, identification, solubility in water and indicator tests. My friends, when we talk about acids, you may remember names of some popular acids such as sulfuric acid, acetic acid and hydrochloric acid. Similarly, examples of bases would be sodium and potassium hydroxide. CaO is also an example. Very popular example of salt is NaCl, as mentioned earlier. Calcium carbonate is also classified as salt, CaCO3. Salts are expected to have a salty taste in general. The most next important point of classification is the taste of the items. Acids, as stated earlier, are mostly sweet. I said it wrong. We all know it by now. Acids are sour in taste. Orange and lemon are sour because of the presence of citric acid. Bases, on the other hand, have a bitter taste. Yes, you heard it right. Bases are bitter, but never try to taste it. So putting all the information on the table would therefore look like this. Acids tasting sour, salts tasting salty, and bases tasting bitter. Now moving over to neutralization. Let's understand what the term means. Neutralization means that acids and bases, when put together, can cancel each other's effects to make a solution neutral. A neutral solution tastes neither sour nor bitter because of the effects of acids and bases that cancel out. How does the property of the solution change when acids and bases are put together? Well, with neutralization, acids react with bases and a chemical reaction takes place. The sour taste of an acid is neutralized by a base and the bitter taste of a base is neutralized by an acid. So far so good, my friends. We have understood differences based on taste and neutralization. Remember The famous equation of neutralization in chemistry illustrates how acids combine with bases to form salt and water. This is the famous equation where positive sodium ions react with negative chloride and result to salt and water. The next property that we shall be looking at is identification. How do we identify acids and bases? One significant feature of acids is that they contain H+ ions. However, it is not true that all compounds that contain H ions are acidic. A very simple example is H2O or water. So you need to be careful when you identify acids. Having hydrogen ions is necessary but not sufficient. The hydrogen ions need to be replaceable. When hydrogen ions are replaceable, they can combine with bases to form salt and water or undergo neutralization. Bases, on the other hand, contain metal oxides, metal hydroxides. If you're looking for a non-metal hydroxide, it could also be ammonium hydroxide. Bases are generally slippery or soapy. If we look at the solubility of the solutions, we will need to dissolve the acids in water and then see the effect. Remember, acids easily dissolve in water to release hydrogen ions, or more correctly, hydronium ions. Bases are, however, mostly not soluble in water, but there may be exceptions. Remember, bases are mostly non-soluble. However, those that are soluble are called alkalis. Examples are NaOH, KOH, and NH4OH. Some again show properties of low solubility, just as calcium hydroxide and magnesium hydroxide. The two kinds of salt previously discussed in the videos were calcium carbonate and sodium chloride. If you take 2 glasses and mix sodium chloride in one and calcium carbonate in another, we will observe that calcium is insoluble, whereas sodium chloride dissolves. The dashboard can now be updated with solubility features. The most important characteristic are the indicator tests that will test for the acidity or the alkalinity of a solution. An indicator is one that typically changes color when dipped in an acid or base. With neutral solutions, there are no reactions. Two most famous indicators are litmus papers and phenolphthalein indicator. These indicators generally show different results with acids and bases. In case of acids, the blue litmus paper turns red, and for the base, the red litmus paper turns blue. In case of salts, there is no change. If you have 3 solutions in 3 glasses and test with litmus papers, you will see the color changes in case of acids and alkalis. With the phenolphthalein indicator, however, it is easier to remember. The only visible change is with the base turning pink, and there is no difference of color for acids and salt. China rose is also often used as an indicator. Acids turn it to magenta and bases turn it to green. China rose is also a very commonly used indicator. So once again, coming back to the dashboard, we can upgrade the results to see how the acids and bases are identified through indicator test. So with this, we complete the table of differences. Hopefully, by now, you have a good understanding of the differences between acids, bases, and salts. Before we end this chapter, my friends, just remember that neutralization of acids and salts are not always chemical reactions visible in the labs only. Some real-life examples of neutralization are indigestion. It's common to suffer from indigestion, and when it happens, we commonly say that it's excessive acidity in the stomach. To neutralize the acid, under such circumstances, we take antacids like milk of magnesia, which is nothing but magnesium hydroxide. This neutralizes the acid and we feel relieved. In agriculture, soil treatment is done with acids and bases. If soil is acidic, alkali is used and vice versa to neutralize the soil. Common examples of bases are quicklime or slaked lime, and you may have seen lime being used to treat soils in villages. Here we see some more examples of acids and bases as key ingredients of some substances. Lactic acid is present in curds, making the taste sour. Remember, lime water has calcium hydroxide and soap has sodium or potassium hydroxide. Ants sting itches because of formic acid, and fruits like grapes and mangoes contain tartaric acid. The key takeaways from the chapter has been listed in the table and mentions the principal differences between acids and bases. So this brings us to the end of the chapter on acids, bases and salts. We hope you have enjoyed the video and look forward to meeting you again in our other videos.